Okay, all right.
Okay. They said that was going to happen.
All right, I will. All right, quiet down now, quiet down. Hi there. Okay. On behalf of the Land Conservation Committee, I want to welcome Alex Bartholomew, a professor of geology from SUNY. Alex is very, very knowledgeable about this area, this subject, but in particular, the Mohonk Preserve, where he is on the board.
Not quite.
Of the Millbrook Preserve,
Millbrook
excuse me,
Preserve, there we go.
Millbrook Preserve.
Yeah, that one,
Millbrook
yeah.
Preserve. And if you're ever on the trails, you'll see him down there very frequently, whether he's cutting down a tree or cleaning up a thing or rerouting a trail
Yeah.
too.
Carrying a child.
He's a terrific guy, and I think you'll have a terrific presentation from him. So welcome, Alex. But here it is, the Pac Evacuation Policy. I have to read it, so here goes. When the alarm has activated, the event facilitator will call the concierge desk at extension 5600 or 0 to find out whether or not to evacuate. If evacuation is determined, the event facilitator will initiate the evacuation as follows. Please exit the room immediately using either of the two sets of double doors and immediately clear the hallway between pool and pack. First to evacuate should be any residents walking unassisted or with a cane. All residents who have a walker, wheelchair, or electric cart should evacuate last with assistance. Once the room is cleared, the facilitator of the meeting will shut both sets of double doors and report cleared status to the concierge. Welcome, Alex.
Thank you. Just gonna. Oh, yes. Are there lights that could be put down a bit? Okay. Oh, wonderful. Okay. Now, hopefully most of this will be eminently more readable than the horrible gray text at the bottom. I apologize. Thank you very much for having me here. As Paul said, I teach one of the professors of geology at SUNY, and I grew up in upstate New York, not too far from Howe Caverns in Schoharie County, and I've had a love of geology of New York State, especially ever since I was a young child collecting fossils and stuff like that. And I'm very, very lucky that when I graduated from graduate school, where I went for 6 years in Cincinnati, Ohio, that a job opened up here at SUNY New Paltz, and I was able to secure that job and have been here since 2006. My specialty is geologic time, historical geology, and sedimentology, stratigraphy, and paleontology. So in other words, I look at fossils and soft rocks, as we call them, things like sandstones and shales, and especially in Eastern New York State and mostly Eastern United States. So today I have a lot of slides to go through, but most of them are kind of maps that I'll just cycle through. We're gonna basically look at time along the East Coast of North America, at New York State in particular, and focus in on the geology of Ulster County and southeastern New York State. So why do I think New York State is one of the best places to do geology in North America, if not really the world? And it's because the geology of New York State is very varied. There's a lot to see in New York State. There's a lot of good exposure. In other words, places where you can go up and hit a rock with a hammer and see things. New York has a neat history of geology. There's a lot of geologic time recorded here. And there's things like Niagara Falls, the Adirondacks. The world's oldest fossil forest is known from New York State. And if you follow any of the kind of updates of the science of geology and paleontology, we found an even older layer of that fossil forest just a couple of years ago around Cairo. We have the Grand Canyon of the East at Letchworth Park, the highest waterfalls east of the Mississippi near Ithaca in Trumansburg is Taganic Falls. Even New York City has some very amazing geology that you can see in Central Park. And then even this picture of New York is taken, I think, from around the Empire State Building looking south. towards the financial district. And when you look at the geology of New York City, you see that in the distribution of buildings, you've got tall buildings in the financial district, tall buildings up around Midtown, and in between are lower buildings. And there's a bit of a twofold reason for that. One of them, though, is the geology, in that you have hard rocks that can support big foundations for tall buildings in those two places. And in the other places, you've got softer rocks, which cannot support those big, tall buildings as well. It also has to do with the developmental history of New York City. And then Long Island. Most of our students, a large population of our students from New York City, from SUNY New Paltz, are from Long Island. And I always like to tell them that, oh, you live on a pile of junk that was scraped off of Connecticut, just tease them a little bit. But it's a really neat story, Long Island, which I think you'll hear more about in a few weeks, and the geology talk about the superficial geology and glacial history. But Long Island is basically a big bulldozer pile, two piles really, of stuff that was pushed off of New England and then left out just slightly offshore in the Atlantic Ocean. So we're gonna focus on the area around here in kind of southeastern New York State for the most part, but just New York State is really amazing in its geology, and it's a great place to teach geology, because in New Paltz, teaching here, we can drive over to the Tectonics, the Catskills, down to the Hudson Highlands, and up into the Adirondacks within a day or so, and take our students all around to see amazing things. So first off, we're going to be dealing with time and deep time. My wife is an astronomy professor at SUNY New Paltz. And she always likes to tease me, oh, you guys don't deal with deep time. So 14 billion years. Okay, sorry, we've got 4.5 billion years. All right, you got 10 more billion years than we do, but you've got no record of it, at least in rocks. You can maybe look at some light or something. But anyway, these are the debates we had at home before we have children. Now we just argue over who gets to change the poopy diapers. But so when you look at rocks are the record of Earth history. And it's the rocks that tell us the story about what has happened on Earth. And we talk about geological time. And Paul's very kind to show me a copy of a book he has here called Strata, William Smith's Geological Maps, a very interesting book. And our understanding of deep time is a relatively new understanding in kind of scientific thought. For a long time, people thought about things with sort of biblical interpretations, at least in Western cultures. And it wasn't until the 1700s and really what we call the Scottish Renaissance, when you had people starting to think about, or Scottish Enlightenment, I should say, when people started to think about the Earth might be older than 404,000 years or something like that. And so we started to look at the rocks and recognize that different rocks had different fossils in them, and that we could differentiate intervals of time without having to know exactly maybe how old they were, but we can say this is older than that. This happened on a Tuesday, this happened on a Wednesday. That sort of being able to tell time, what we call relative time, not applying a number to things, but saying this happened before that happened, is really a very critical tool in our understanding of creating a history of the Earth. And so we developed over time what is called the geological time scale. And we have a lot of different names for different chunks of time, but importantly, we have kind of two major intervals of time in Earth history. And as living beings, we are very biological centric. And so we have what we call the Phanerozoic, which is Latin meaning you can see it life, visible life. And then we have all of Earth history before that we just call the pre-Cambrian. And people thought that there weren't fossils around back here. There wasn't life. We now know that there was, and as we begin to see things better and look at things with microscopes and be able to interpret more complicated rocks, we can see that there was life back in there. But this broad break right here at about 550 million years ago is when we really start to see fossils of organisms that look like things that are maybe around today, all right? Shells and things like that. And so then we take this time of visible life and we split it up into the Paleo, Meso, and Cenozoic, which means old, middle, and young life. And the breaks between these are at big, what we call mass extinctions. And you've heard of these, I'm sure, when a lot of different things on Earth kind of all died in a short period of time. So the major breaks between the old life, the middle life, and the young life time periods are when we had big extinctions. Of course, the one here at the end of the Mesozoic is what killed off all of the big dinosaurs. And the one here at the end of the Paleozoic was actually the biggest one in Earth history. And it's estimated that around 90 to 95% of all different types of life in the Earth's oceans went extinct in a very short period of time right there. So our understanding of fossils and the record of life on Earth is critical to our understanding of time on Earth. And so we can think about this time. We have the Precambrian, which is a very long period of time. This kind of puts it onto like a clock face, sort of. And we would say that human history is recorded in like the last second or so of the last hour, or the last minute of the last hour of right before midnight, right? And so our human history record is very short, but the record of life on Earth is very long. So we can split up the time into these different chunks. I'm not going to go into all the different names of them right now, but we'll kind of march our way through a lot of this. We're going to start, New York's record starts somewhere here in the Precambrian. And let me go back here for just a second. So one of the important things that we think about in modern geological thought is how the continents have moved around the globe. And this idea of plate tectonics. And I was chatting with Paul when I first got here. And plate tectonics, you've probably mostly heard about how the different plates, the pieces of the Earth's crust, move around and shift their location. Oceans can open up and oceans can close. Right now, the Atlantic Ocean is currently opening. We're getting farther away from England at about the rate at which your fingernails or hair grows. And the Pacific Ocean is closing. And so we're getting closer to Asia at about the same rate. But this is new, as in like, we didn't really know about how it worked until the 1960s, right? And the history of how that was found out was actually pretty interesting. And I got to hear a talk by a fellow once in grad school who was really one of the first people to come up with the way plate tectonics worked. People looked at the edge of Africa and the edge of South America. There's a famous geologist named Werner who was sick supposedly one day, and he was looking at a map, and he said to his friend, "Hey, bring me a pair of scissors." And he started cutting out the edges of the continents. And he said, "Hey, look at this. South America fits right next to Africa. Isn't that weird?" Right? And then, so this was the idea of continental drift. And so we thought the continents moved around, but we didn't have a mechanism to explain it. And then after World War II, when people were trying to clear the North Atlantic sea lanes of mines that were put out by the Germans to block merchant marines and stuff transporting goods across the ocean, they were using magnetic readers, and they were looking for the mines out in the ocean, and they started noticing that there were these weird bands of magnetic stripes on the oceanic crust. And then they said, "Hey, wait a minute. If you cross the mid-ocean ridge, which is this big kind of underwater mountain chain of which Iceland is a part, that you see the same pattern on either side of the ridge, like a barcode on the back of a grocery that you buy." And they said, "Hey, we think that the ocean crust is spreading here at the mid-ocean ridge." And so we finally got this mechanism that could explain the pattern that somebody had noticed half a century or more earlier. And so finally, to get back to this slide, we talk about what we call supercontinent cycles. Maybe you've seen the bumper sticker, Reunite Pangea. All right, you've heard of Pangea, maybe it's a supercontinent. About 250 million years ago or so, almost all of the continents, all the continental land masses were in one big pile. And they subsequently split up into the different continental pieces that we have today. But it's not the only time this happened. If you go back to about 1 billion years ago, you had another, what we call supercontinent, and that was a supercontinent called Rodinia. And so New York's geological history starts with kind of the building of this supercontinent called Rodinia a little over 1 billion or so years ago. And so if we look at New York State and the different kind of, we call physiographic provinces, which is, we mean the different ways in which the land looks in New York State. You've got the Adirondacks up here, which are some of the oldest rocks in New York State. Also, some of these old rocks are exposed down here in the Hudson Highlands, down around Storm King and Breakneck Ridge, Newburgh and areas there. And then you have the Catskills here. We are in the Gunks right along here around the edge of the Catskills, the Hudson Valley, the Tectonics, and those mountains are their own separate story. And then the Allegheny Plateau over here and some other areas. What you'll notice as I shift to the next slide is that this pattern basically matches this color pattern on this map, which shows you the geological age of the rocks. And so the Adirondacks and the Hudson Highlands are some of the oldest rocks we have. And then we have the rocks that surround the Adirondacks and the Mohawk Valley and the Hudson Valley, the Tectonics over here. And then the youngest rocks we have in New York are up here in the Catskills for the most part, but then also this one little blob down here in Rockland County that I'll talk about near the end of my talk. So you can then, geologists never like anything simple, so we can go in and bust up that time into even smaller time slices, and we can make more complicated geological maps. The history of New York is really one of mountain building. And New York State was at one time right along the edge of the North American continent, or what was called Proto-North America. And by that, I mean that all of New England didn't exist early on in New York State's geological history. And so we had different times of continental collision that resulted in the formation of the rocks that we have in New York State. And so we can look at this history of mountain building, and it starts way back about 1 billion years ago with what we call the Grenville Orogeny, which was a mountain building event. And that's what this fancy term orogeny means mountain building. And so the Grenville mountain building event takes place about 1 billion years ago. And then we have the Tectonic Orogeny, which happened about 450 million years ago. And then another one called the Acadian Erogeny, which results in the Catskill Mountains. And then there's even a third one or fourth one called the Alleghenian Orogeny. And this is when Africa collided with North America. So we are going to look at this history of kind of continued collision of pieces of continental crust with North America as recorded here in New York State. And so if we look at a cross section here just of Ulster County, what you can see are the effects of these mountain building events. Here's the Hudson River. Here's the Wallkill Valley. And New Paltz is somewhere here. Up here is the ridge of, wait a minute, what happened? How did I do? Okay, sorry. There we go. Okay, here is the ridge of the Gunks, Rondout Creek behind that. And then you go up into the Catskills. And the rocks that we have in New Paltz, if you've ever seen any exposures of bedrock around town, and they're kind of low and scrappy. There's a few in the Millbrook Preserve that I look at, like, oh, here's the outcrop on the Blue Trail. All right. But it's all mostly shale and sandstone, but it's all crumpled and folded. That's from the Tectonic Orogeny. And the gunks that you have here are their own, the result of their own mountain building event, which took place after the Tectonic Orogeny. And then we go into the rocks of the Catskills, and that's the Acadian Orogeny. So right here in Ulster County, we have the effect of two of these mountain building events that are very interesting and very kind of difficult to tease apart. We're still working on a lot of this. So we're going to start here in the Adirondacks in the Hudson Highlands. And I've got a bunch of these maps. These are what are called Paleogeographic Reconstructions. And this is a pretty neat job in geology to synthesize the work of hundreds of geologists and try and put together a map of what we think the Earth looked like a long time ago. And so this is about a billion or so years ago. Well, latest Precambrian, maybe 750 million years ago. But you can see that most of the continents are centered over the kind of the southern part of the globe, unlike today, where most of the continents are in the northern part of the globe. And you had some big oceans here. So we are going to look at this. Well, what can we talk about in the United States and North America, what we call the Laurentian Craton? We'll use this term craton, all right? Craton means the core of the North American crust, or any continent has kind of a core at the middle of it, which are the oldest rocks. And then as you get towards the edges of the continents, they've got younger and younger rocks that make up the edges of the continents. And a lot of these rocks are exposed up here in what we call the Canadian Shield. And they are exposed, meaning you can walk up to them and see them today, because the glaciers scraped off the top of most of Canada, cut very deeply down into the bedrock there. And we can look at the edge of these rocks. We have some of them right here in New York State that are exposed up in the Catskills, or I should say the Adirondacks, excuse me. And so if we look at the core of North America, we can see that it's made up of a number of different chunks that have varying ages. The GA here stands for gigaannum, which means billion years old. And we are in this province that we call here the Grenville Province. So along the eastern and southern margin of North America, about a billion years ago, there was a big mountain building event where we think part of northern South America and Western Africa collided with North America. Now you're going to say, how in the world do you know that part of the Amazon crust of northern South America hit North America? And the answer is, I'll tell you in a few slides. So you have this Grenville province that goes all along the eastern side of North America. And it was a monstrous mountain building event. I mean, Africa and South America, they're big chunks hitting other big chunks, being North America. And so we look at the Adirondacks, and they are roughly circular in region, about 200 kilometers in diameter. There is a central highlands, which makes up the highest region of New York State, Mount Marcy, of course, being the highest mountain, over 1,600 meters tall. And then you have the Northwest Lowlands, which are kind of up by Oswego in that area. And they are a little bit lower in height up there. So here is a satellite view of New York State. This is the Mohawk River. Here's the Sacandaga Reservoir, Lake George, Lake Champlain, the Adirondacks, and these are the Central Highlands, and then the Northwest Lowlands kind of go off like this. You see a radial drainage pattern. So this is kind of interesting. If you look at the way the rivers are draining off of the Adirondacks, they kind of all drain away from the high points. And this is a weird thing. The Adirondacks are the oldest rocks in New York. They're, like I say, about 1 billion years old in age. But as far as mountains go, they are the youngest mountains in New York. And in fact, the Adirondacks at their high points are rising on the scale of millimeters per year. which is really, really fast in geological time. They're going up quite a bit. So they're very young, having pushed up through the rocks that are on top of them. And this old stuff is being pushed up from below. We're not exactly sure why that's the case. There may be something hot under there coming up from deeper down inside the earth. We don't know, but there are a lot of earthquakes and we can measure the uplift rates. And this radial drainage pattern where all the streams kind of drain away from the high point supports that being a relatively young mountain building event. So this slide is just a fancy way of explaining that there was a lot going on here during this mountain building event that created the Grenville mountain building. There were probably 2 or 3 times of collision that occurred up in the Adirondacks. And perhaps one of the neatest things is that we can tell how deep the Adirondacks were buried, because we can look at some of the minerals that we find in there, and we can know that those minerals change based upon experiments that we can do in the lab. And we can say, okay, at what temperature do those minerals change in the lab? And then we can go out into nature and say, okay, how deep does it have to be buried to get to that temperature? And so we can say that in the Central Highlands, that the rocks indicate that they were subjected to temperatures around 750 to 800 degrees centigrade, really super hot. And that means they had to be buried 25 to 30 kilometers down in the crust. And so if you think about it, that means that they were really deep in the Earth's crust, and then they had to get all the stuff taken off on top, like a pile of plates in like a cafeteria where you keep pulling the plate off the top as everybody comes through, and the bottom of the plates keep rising up, just like that with these mountains. So the Northwest lowlands were buried a little bit more shallowly, but the Adirondacks once lay beneath a full thickness of what we call continental crust. They were buried very deeply, and a lot of material has been taken off of the top of those mountains. The Hudson Highlands down in the southern Hudson Valley are rocks of the same age, and they're not as high as the Adirondacks, but they're still really high, because remember that the Hudson River is at sea level at 0 meters. And so right next to that are mountains that are 400 and so meters higher. That's pretty darn high. This is where we know that parts of South America hit here. By the way, we're talking about this area right down in here, just north of the Tappan Zee. And in fact, if you look at the width of the Hudson River, here's the Tappan Zee, which is kind of Dutch for Sea of Tapan. Somebody named Tapan must have lived there. And then just north of that is the Hudson Highlands. And then up here is a pretty wide spot in the Hudson River. But when the Hudson River cut through the Hudson Highlands, the rocks are very hard. And so the river gets very narrow right through there. And if we look at the Hudson Highlands, we can find some mineral crystals that we know by looking at the chemistry of those crystals. The only other place on the planet where we find crystals with the same chemical, we say chemical fingerprint because it's unique, is from South America. And so that's how we know that South America was most likely the culprit for the big collision. What car hit what other car? And we can, just like a forensic criminologist, look at the chemistry of the paint that's on the 2 car collisions. We can look at the chemistry of the minerals that we find and try and figure out what model of continent hit North America. We've also got some important minerals that are down there. And if you've ever been to a place called Franklin, New Jersey, it's a really cool place, and they have a really nice museum with all these glow-in-the-dark minerals. They're fluorescent minerals. And they have more different types of minerals there in Franklin, New Jersey than just about anywhere else on Earth in one single place. And that's its own really crazy story there. After the Grenville Orogeny happened, and we make this supercontinent of Rodinia, when you've got all these continental land masses in one pile, they don't like to stick around in one pile for very long, and they start to split apart. So North America and Rodinia now starts to break apart. And we call this rifting. where the one continent moves one way and one continent moves the other way. And so between around 650 and 600 million years ago, a little over 500 million years ago, we produced a number of faults and expansional valleys all across New York State. And if I can back up here to this map, if you look at this view of the Adirondacks, you will notice that there are these kind of trends that go like this in the cracks, right? A lot of the lakes are oriented kind of about north, northeast, south, southwest. This is what's called, in a fancy geological term, a structural lineament, meaning that we've got all these cracks that are kind of all lined up. And this is because as we pull apart North America, it doesn't break in just one simple break. There's a number of breaks that begin to split apart, kind of all next to one another. And so we can see that all these little breaks up and down in the Adirondacks. Okay, so map. Okay, so now we jump forward to what we call the Cambrian. Now we are in the time when we have really good evidence for fossil life on Earth. And we have a big chunk of missing time. I have a really nice analogy that I like to use when I teach this, and I'm beginning to feel that it is completely lost on my students, but I think I've got the right crowd here. Do you guys remember Watergate? My students are like, who? Right? So, and also when I try and talk about cassette tapes, they have no idea. I still had a record player when I was a kid. But then I got cassette tapes. But you know the Watergate tapes, the problem is there's this missing chunk of time with 19 minutes or something, right? So 18 minutes? Yeah. So there's missing time in the rock record. It's not that there's 18 minutes of blank tape, right? It's not like they just shut off the microphone. No, they stopped the recording. So the conversation is going along and then it jumps, right, forward, and their conversation picks up again. It's the same way in the rock record. We've got these rocks that are about 1 billion years old, and then sitting right on top of them are rocks that are about 500 or 450 million years old. And you can walk right up to the cliff and you can put your fingers on either side of this crack that represents 550 or 650 million years of time. I tell my students, this is mind blowing, right? Between my fingers is more missing time than the oldest rock on top of it till now, all right? There's 650 million years missing at this crack, and the rocks on top of it are only 550 million years old. So there's a lot of missing time in New York. The geologic record is not perfect. We have to deal with what we can. We piece it together as best we can. And if you've got missing time, what you need to do is go somewhere else on Earth and try and find rocks from that missing time to piece together the story. We can try as well as we can to put it together, but it's an imperfect puzzle. There's always missing pieces. So we jump ahead now to this younger time in New York State. And now is when we begin to have a really good record of the history of New York State. And so, let's see, we break up Rodinia. We break up this supercontinent that was around about 1 billion years ago. And we are ended up with kind of this zigzag margin to it. And so we have what we call the New York Promontory that sticks out here. And it goes up pretty much along the Hudson River up to Lake Champlain. And then it kind of kicks out along the St. Lawrence River. And so any land that is east of just about the Hudson River or Lake Champlain and kind of southeast of the Champlain or of the St. Lawrence River has all been added on to the east edge of North America. If you wanted to buy oceanfront property 500 million years ago, you went to Lake George, right? It's crazy to think about, but that's where the edge of the ocean was. And all the stuff that's east of there got smacked on to the east side of North America later. So here you go. Now we're going to look at these maps. These are made by a guy named Ron Blakey, who was at the University of Northern Arizona. And he does a really nice job with these maps. And these ones here, he orients with North America kind of it is today, and he puts the state outlines on it. And so you can see about 550 million years ago, the eastern edge of North America runs pretty much right up along the eastern New York State border. So you have all of these we call buried block faults, all of those kind of, we call them collateral rifts. When Rodinia split apart, all those kind of side split aparts that happened are buried under the rocks that we have here at the surface now. And so this is showing you the opening of this ocean. Here's proto-North America. And then this land over here was probably part of Europe or South America. And we're opening up this ocean that we give it the name, the Iapetus Ocean. We also sometimes call it the Proto-Atlantic because it was around before the Atlantic. And we get into the early Cambrian. And what do we see in New York State? We have an area of low relief where you've got exposure to the air. And then you pretty much had a beach that was covering our area that ran along up through where Vermont is, Massachusetts, and then kind of down through about Troy and kind of along the edge of the gunks here. And offshore of that, you had nice limestones. Think the Bahamas, Florida, all right? At this time, North America was straddling the equator. And if I were to, can I do this? Let's see. Ink, aha, I can. Let's see if I can do this. Okay, yeah. Roughly, that's where the equator was. All right. So here's the thing. You got to take this map that Blakey has made really nicely, and he orients it where North America is today. And you got to think, okay, but he's got the whole map tilted about 45 degrees. If you bend it back down so the equator is flat like it is today, North America is kind of tilted about 45, 90 degrees, and the equator sort of runs through northern North America. So where we are here in New York State, maybe 15, 20 degrees south of the equator. And so it's a nice shallow water, warm area in New York State. Sea level begins to rise, and we worried about this today, sea level rising, we melt the polar ice caps, what's going to happen? Albany is at sea level, right? I was talking about this in my class yesterday. The tide goes up and down a meter at Albany, some 150 kilometers, 200 kilometers north of New York City. If sea level goes up a meter, you're going to lose part of Albany, way up there, right? So sea level starts to go up, and what happens is that beach moves inland, and we start to get covered with limestone here in our area of Ulster County. So if you go down to Orange County, Rockland County, you can see some of these nice limestones exposed, also over in Dutchess County to some extent. Here, they're buried underground. We don't have them at the surface. Then we get into this time that we call the Ordovician. This is named for a tribe of pre-Roman people that lived in southwestern England, and we're up to maybe around 480, 450 million years ago. But you start to see this, which kind of looks like Japan off of the eastern margin of Asia. These are the Tectonics. These are the tectonic, what we call the Island Ark. And it's the same story of what's happening in Japan today, where you're starting to take the eastern edge of North America and send it under oceanic crust. And as it begins to go down, we call this subduction, where one plate goes under another. It starts to get hotter and hotter as it goes down into the earth. The rocks start to melt, they start to go up, and you get volcanoes somewhere offshore. And so you had, it was starting to get pretty deep off the eastern margin of New York State over in Massachusetts and Connecticut at this time. And then eventually we start to see, as we kind of conveyor belt down the eastern side of North America, the volcanic islands get closer and closer and closer to New York State until such time as we have our first mountain building event of the Paleozoic, about 450 million years ago. And so I'm gonna go with here. So here is about the late Cambrian. You can see this is just before the Tectonic Orogeny, and you have deep ocean waters that's kind of over in Massachusetts and Connecticut, and you go up onto we call it a shelf of pretty shallow water limestone here along the eastern side of North America. And then the first kind of phase of this is the development of some volcanoes. And we know that they were volcanoes because they produce what are called pillow lavas, which is where volcanic rock is extruded out of the ground, but underwater. And it freezes right on the outside, and you get these weird things that look like big blobs of lava that solidify into basalt. And you can see this up at a place called Stark's Knob, which is just north of Saratoga. And this was a place when they had the Battle of Saratoga in the Revolutionary War. This was an observation point there. And so you had volcanic rocks, which were being kind of falling down and going off into the oceanic basin that was at the edge of North America. And these ultimately get pushed up onto the edge of New York State, just like kind of a snowplow pushes a big pile of snow in front of it, or the glaciers push a big pile of sediment, and it shoves it up onto eastern New York State. And so we begin to flex the edge of North America down as you load it. Imagine a kid walking out on a diving board, and the diving board end goes down. So as you start to load the edge of North America, you make the water deeper and deeper and deeper. And you start to see then shale and fine grained muds that get deposited. And these are the first rocks that we have here in New Paltz. The shale and sandstone that makes up the bedrock right here under us at Woodland Pond was deposited in front of these volcanoes that were over in Vermont and eastern Massachusetts. And they were mountains that were tall, and they were weathering and eroding. Streams were carrying mud out of those volcanoes and depositing it in the oceanic basin that was along the eastern edge of New York State. And so here's a nice cross section. These is over in Worcester, Mass, and these are the Tectonic Four Arc Basin, we call it, and then the shelf kind of up around Albany. And so as you push down this eastern side of North America, you create a big, deep swimming pool that can then fill up with mud. And so it completely fills in. You completely fill this in until such time as the whole thing crashes together. And now here's the New York, Massachusetts border. And you've got all these rocks that were kind of caught up in the snowplow in front of the Island Ark that was coming in. And you completely fill the ocean basin that you make because you've got so much sediment eroding coming off of those mountains, and you fill it all in. And eventually you get to what we call the Queenston Delta, where now all of New York State is terrestrial. We say it's like land sediment, and there's mountains here that are carrying the sediment across New York State all the way out into an ocean that was now like over in Ontario and Ohio. And so then we get to a time period that we call the Silurian, and this is named after another tribe in England. And the Silurian is pretty cool because now we've got the end of that mountain building event, and we return to kind of quiet water conditions on the east coast of North America. And we have some really amazing fossils in the Silurian period in New York State. In our area, the Silurian is best exposed up around Kingston and down by Rosendale, and it's where all the cement comes from in Rosendale that I'll talk about just at the end. But it's got some pretty cool fossils in it, including these things called Eurypterids, which were like giant horseshoe crab kind of relatives that are extinct today. But they were big. Some of them were up to 2 meters long. And they were some of the biggest invertebrates ever. If you've ever seen the movie Them with the giant ants, all right, from the 50s, that can't really happen because those ants, their body would collapse under their own weight in the air. But if you put them in the water, you've got the buoying effect of the water, and they can get that big. So these were like ants, like the size of that from Them, but they're like giant horseshoe crabs. Scary looking, but pretty cool. And so we find a lot of these in New York State. A lot of them are pretty small, but you do get rarely these really big ones. On land at this time, we start to see the development of plants. Here's something. Before this time, we had no plants on land, no crickets, no bugs around to chirp or crawl around, nothing to eat. Land was just dirt being eroded away, wind blowing, water carrying it away. There's nothing to hold any soils around. In the latest part of the Silurian, we kind of have a bit of rejuvenation of that mountain building event that took place in the Tectonics. And we see the mountains start to erode one last little pulse of sediment. And what is that sediment? It's the gunks, all right? So the gunks are probably, well, they're made out of a lot of quartz conglomerate, which means big pebble pieces and sand that were carried off of the end of the Tectonic Orogeny, the end of those tectonic mountains over in Massachusetts and Connecticut. And they were carried by rivers and streams right over to New Paltz and kind of points west a little bit, dumping out into an ocean that existed in New York State that kind of went from New Paltz was about the beach at that time, extending in this ocean that went over to really all the way into Ohio and almost Iowa. And then we can jump into a time period that I really like that is called the Devonian, named for Devonshire in southern England. And New York has some incredible Devonian rocks in it. And we are now in between the Tectonic Orogeny and the next one called the Acadian Orogeny. And the Acadian Orogeny starts, and this is another chunk that kind of comes conveying belt into North America and starts to push down again the eastern side of North America. And we build what we call the Catskill Delta. So the Catskills, you may have heard this term, that the Catskills aren't really mountains. They're a dissected plateau. All right, this is when geologists get fancy and start to argue with one another because everybody likes to be right about something. Mountains are high areas of land. Okay, now how you get those high areas of land? Well, you can push the stuff up from beneath, like the Adirondacks, or you can have something that's high and you cut down into it and you leave it behind as something that's high. They're mountains nonetheless. So the Catskills, as opposed to being something that gets pushed up from below, were this big pile of sediment. And I'm talking like kilometers thick of sand and shale and mud and gravel that came off of the Acadian Mountains, which now you had slammed this land into the east side of North America. And you now jump kind of the eastern margin of North America over to about western or eastern Massachusetts and New Hampshire. And then the next collision that occurs happens over in New Hampshire and Maine. And so you've got these big mountains over in New Hampshire and Maine that are carrying sediment across to New York State. And so here's a nice view that my friend Gordon Baird out at SUNY Fredonia has drawn. And you can see the mountains here and the streams building out. And we call it the Catskill Delta because we think it was a big pile of sediment, just like the Mississippi Delta, that was being carried out into this ocean that existed in New York State. And on this delta is where we find some of the oldest plant fossil, well, not plant fossil, but the oldest fossil forest ecosystems in the world. And so this is the Gilboa Forest as we understand it. And I grew up in Schoharie County, and Gilboa is in southern Schoharie County, and I did my master's work on this. And so these were weird trees that had kind of big bulbous bottoms. They didn't have roots that went straight down, really. They're more kind of like a giant mangrove that kind of had roots that stuck off the side and a big bulb at the bottom. They stood to be about 30 or 40 feet tall, and mostly they grew in kind of swampy environments with a lot of different types of fish that swam around in there. So we find a bunch of fish fossils. These were discovered when the New York City water supply system was being developed in the northern Catskills, and they made a quarry there in the 1920s. They were discovered actually in a flood in 1869, but then when they made this quarry in the 20s, they found hundreds of them. And they took them out and they sent them all over the world. So there's a lot. We're up at the State Museum in New York State, in Albany. And so this was a reconstruction that was done of them. Mostly they are tree stumps. The biggest one is about 1.5 meters tall. And this is kind of looking down onto the where we think one of them sat. And you can see the strappy roots going out from the side. And then this is one in cross section. These were preserved in floods on the Delta, where when you had a time of sea level rise, you could back up the mouths of the rivers and sediment would come dumping out onto the sides, just like Hurricane Katrina did, where you blew out the levees and you had all this sediment and mud that was deposited very quickly. And that's the same thing how we think that the tree stumps were preserved. There's lots of other different types of trees and things that are around in here. A lot of them look like modern day club moss, which you can still find up in the gunks. And some of them were small, some of them were big, like this tree that I think looks like a Dr. Seuss tree. Sigillaria is about 90 feet tall. Archaeopteris is the big one that we have in New York. And you can find these up in the Catskills, pieces of them. Early land animals, the importance of I kind of shouted that, sorry. The importance, I get excited about the Gilboa Forest. The importance of the Gilboa Forest is not that it's old trees, but it's an old ecosystem. So we don't just have trees, but we've got things that lived in the forest and they're all preserved. So you've got things like very early spiders and other arthropods like spiders. You've got the oldest centipede in the world is from Gilboa, and some very old fossil mites that are there. And these are this is a modern centipede, and this is one from Gilboa. And so the preservation on these is like incredible. And they were probably deposited in a swamp, and they just are preserved very pristinely because they weren't subjected to a lot of heat or anything after they were preserved. As we go up into the Catskills and continue up into the Catskills, we get into what we call the upper part of the Devonian. And we're starting to build again another supercontinent. And so collision continues. And we have the ongoing Acadian Orogeny. And we start to make New York State be deep water again, and especially out in Western New York State. And so here's the Acadian Mountains with meandering streams coming out into a shelf. We would have been in the Eastern Catskills about here. This would be kind of maybe out in the Eastern Finger Lakes and then the Western Finger Lakes, and then out by like Rochester and Buffalo out here. And so if you get out to places like Watkins Glen, you can see a lot of these rocks that were deposited in this deeper water environment, while we here in the Eastern Catskills had things like the Gilboa Forest growing. And there were a lot of fish out there as well, like this giant guy called Dunkleosteus. And this is probably about life size for this thing. This was a really big fish. They're not around today. They were called arthrodires, and they had a skeleton on the outside of their head, kind of as opposed to inside the skin. And they had these big shearing plates, and these were really the top predator in the seas at this time. And then I'm just gonna blop through these slides. You can see that here we are in the Mississippian. This is about 340 million years ago, 300 million years ago, and now 280 million years ago. We're really starting to build this giant supercontinent of Pangaea. And this is when Africa collides with North America. We don't have really a record of this in the form of sediment in New York State because it was all above sea level. And we weren't able to preserve much rock at this time. Everything was eroding away at this time. But we get into the Mesozoic, and now we have the time of dinosaurs, and we've completely built Pangaea here, and it's kind of shaped like a big C. The only place that really wasn't connected was a bit of, I think this is called Kazakhstania and South China. Bits of Kazakhstan and what are now Kazakhstan and South China were a little bit on their own, but the rest of this is North America. This is South America and Africa. Here is India, Madagascar, Antarctica, and parts of Australia. And then you go up, this is Europe, Here's the Ural Mountains here. And then this is Asia. And then this is kind of East Asia, which is going to kind of rotate in like that. So now we've got this giant supercontinent, and we do have, but then again, nothing stays around too long like that as a big bit of oceanic or continental crust. It begins to pull apart. And this is the beginning of the opening of the Atlantic Ocean. So here you can see this is West Africa, Northern South America, and we begin to pull apart this giant supercontinent. And so the way this happens is that you've got a hot, what we call a mantle upwelling, deep in the Earth's crust. It gets hot under the continent, and the continent begins to get lifted up, and it starts to pull apart like taffy, and you open an oceanic basin. And this is occurring today right here. I don't know why I drew that, between Eastern Africa and the Arabian Peninsula. And then this is Djibouti and that area here. And then, so this is the Red Sea and the Gulf of Aden here. And so this is moving this way, all right? And then this is moving this way. And we also, have a little bit of movement. This is called the East African Rift Valley. Whenever you have one of these happen, they always tend to happen at what we call a triple junction, one kind of spot. And they tend to arc off at about 120 degrees from one another, right? And so one of them always fails, and the other two always keep going. Not always, but most of the time. And so this is going to be now a new ocean here, and this is going to be a new ocean here. They'll be connected. But the third one, that is the East African Rift Valley, where things like Lucy and these old human fossils come from, that's never going to open up into an ocean. We have one of these in Connecticut that is basically the Connecticut River Valley is kind of we say a failed rift where one of these triple junctions went off and it tried to rift apart New England, but it didn't quite make it all the way. So when you have this and you pull apart the crust, one side kind of drops down and you create now a place to accumulate sediment. And this happened along right down here in southeasternmost New York State. So Rockland County kind of going down into New Jersey, down towards Staten Island. And this is what we call the Newark Basin in New Jersey. And so if you look at it, you've got a fault that you cross right down where 287 and 87 split off around Nanuet, where you can drive down to New Jersey, go down to IKEA or Cantmore or something like that, or you can keep going on down to the Tappan Zee Bridge. And you cross this fault called the Ramapo Fault. And there's a big pile of sediment right there on the other side of that. And if you drive down, next time you drive down there, if you ever do, you're going through the Hudson Highlands, and then out in front of you is this broad, low plain. And that's where you cross that fault of the Ramapo Fault. And you go out into the Newark Basin. And you have accumulation of deposits that were in lakes and on rivers and streams. And this is where we get a lot of brownstone. Like the New York City buildings made out of brownstones are all quarried out of these sandstones from when the Atlantic Ocean initially started to open up. And so in New York State, our record of this is really well exposed in the Palisade Sills along the Hudson River around Nyack. And if you ever take the train that comes Metro North and you look out the window and you look across the river, you get some beautiful views of this down south of West Point. And this is basically a giant intrusion of basalt that came into very shallow crust there. When you start to pull apart the continent, stuff from below squeaks in. And so pieces of deep mantle material were squished up and came out as volcanic flows and lava flows. And some of it, we say intruded into the rock as well. And so that's what the Palisade Sill is. And it's right along the Hudson River around Nyack. So now what do we have as far as life on land at this time and life in New York State? Well, we do have some evidence for dinosaur activity in New York. This guy called Coelophysis was a small dinosaur, about 9 feet long, and it was a carnivore, and we think it hunted in groups. And the evidence we have are not really bones, but we've got a lot of footprints. Not a lot, but some down around Rockland County and Nyack. And especially if you go down into New Jersey, there are a number of fossil footprint places. I have a buddy that teaches at William Patterson University, and whenever they're building houses around where he lives, when the workers quit for the day, he goes into the excavations and he finds dinosaur footprints and stuff. It's really quite amazing. He lives right around the corner from the housewives in New Jersey. And so whenever they build a new house, they build it on dinosaur footprints. Little do they know, right? So you had other things like crocodiles that were around here and some giant salamander-like creatures, and Coelophysis was really the big dinosaur. Not very big, but it's what we've got in New York State. And then we continue to open up the Atlantic Ocean, and this goes on for a while. And that's where my talk as far as geologic time is going to stop, because that's where the record of hard rock geology stops in New York State. I do want to take just a few minutes here at the end, though, to talk about the economic geology of New York, because we do have a lot of natural resources in New York State that are very important, and they were of critical importance for the economic development of Ulster County historically. So the economic geology of New York State is a multi-billion-dollar industry. It's a big industry. It's estimated in 2011, which was the last time we had metrics conducted. They're probably going to be run again in the next year or two. It's about a $5 billion impact of the economic resources on the economy. And there are about $1.87 billion in estimated resources in 2019 in New York State. So the further impact is in employment and permitting and all that kind of stuff that goes into it. And so, of course, you can't think about Ulster County without thinking about the cement industry. And the cement industry is directly tied to the canals that were developed, and the Delaware and Hudson Canal, which is a really neat canal because the Delaware and Hudson Canal was developed to transport coal from the western coal regions of Pennsylvania to New York City. Now, you might say, well, why didn't they just haul it across Pennsylvania? And the answer is the gunks. They had to run a canal that actually went around the gunks. So the gunks, in essence, disappear right around the trestle on the Wallkill Valley Rail Trail. There's a thin, maybe 6 or 7 inch layer north of the trestle that you can find, but south of the trestle, you've still got some gunks that are there decently sized. And that's why the Rondout Creek runs up west of the gunks and then cuts to the east across the top of the gunks there and comes down through Rosendale. And so they made this canal that ran all the way along the west side of the gunks until it got to Rondout Creek, and then it could cut out to the Hudson. And when they made that canal, they discovered that there was limestone and stuff along the sides of the canal that were perfectly suited to make what we call natural cement. You mine it out, you grind it up, and you heat it a little bit to drive off calcium and carbon, and then you make what's called CaO, slake lime. And so the Rosendale cement, of course, was used to make things like the Brooklyn Bridge, and the cement works were huge for about a century in Ulster County. And you have 2 main layers that were mined, the Rosendale and Whiteport members of these latest Silurian. So they're about 420 or so million-year-old limestones. And if you've ever been to the Widow Jane mine, you can see this double-decker mine where you've got one that you can go into, and then there's another one up on top. They were mined with what was called room and pillar mining, where you basically left these pillars to support the roof. And you just mined out as much rock as you possibly could without having it collapse. So the success of this was tied to delivery costs because it's right along the canal that as these canal boats came up, they could just dump the cement on there and send it down the Hudson to New York City. So production grew from 600,000 barrels annually in the mid 1840s to, by the time they had in 1899, almost 10 million barrels produced annually from the cement region in Ulster County. And it accounted for 40% of the US, we call natural cement industry. And it was used to make the Brooklyn Bridge, the footing and pouring of the Statue of Liberty, and then Devil's Island off on the Dry Tortugas west of Key West. So, oh yeah, and you'll see a lot of these things in the woods around the area. These are called kilns. And part of the process of making this was you grind it up and then you would heat it up to drive off carbon and oxygen. I said calcium and oxygen. And you wanted to get what's called CaO, calcium oxide, quicklime. And when you added water back to that, then it would make cement. And so these were where they would pour cement or pour the rocks in the top and then burn a lot of charcoal down here and let it go for about a week. And then they would pull the stuff out and they would have that slaked lime that then they could grind up. The gunks were critical to this too, because the millstones that ground up the cement were mined up in the Shawngums by people who would pick blueberries during the summertime and then make millstones during the wintertime. Clay, also of critical importance, in the clay yards down around Ponconky and East Kingston. Now they're the Hutton Brick Yards. Bob Dylan played there a couple years ago. But these were big clay pits, and it's estimated that in the 1890s, 1.5 million bricks per year were produced down in around East Kingston. And if you ever go to Kingston Point Park, the beach there is just covered with bricks that have washed downstream. Emery, it was mined in the Hudson Highlands as a natural abrasive, and it was used to polish cannons in World War I. But now we can make this man-made, and so we don't mine it anymore. Gravel and sand, though, is the really big one in New York State. It's a multi-billion-dollar industry and accounts for most of the economic industry of New York when it comes to geology. And that's because anytime you make a road or a building, you have to have aggregate that fills up the concrete. And so you have to get that from somewhere. And so it is mostly crushed stone and gravel and limestone that is mined. And a lot of money comes out of this. And a lot of it comes from Suffolk and Dutchess and Rensselaer counties. But Ulster County as well, up around Kingston, is still a producer of this. And so this is a map of where all the sand and gravel mines, all of New York State is basically mined for sand and gravel. There's just tons and tons of these, hundreds of these mines and quarries around New York State. And then bluestone, back to Ulster County for a minute. You may have heard of bluestone. It's a building stone, and it was used for millstones to some extent as well. But in Ulster County in 1895, there were 553 different kind of mom and pop quarries that were run in the woods. Most of them were in kind of western Ulster County. So they would produce flagstone and edgestone and what was called rock, real good name there. And this is one, shows you how times have changed. In this case, this was Sawkill Creek, and they wanted to mine, and so they just made a box and ran the creek through a box. Pretty sure that NCON would not let you do this today, where you just, we're going to put the creek in a box, all right, and just run it through the middle of our quarry. I don't think so. But the economic call for bluestone for building down in New York City was so big at that time that they did it. Slate is mined in the Tectonics. And a lot of slate used in roofs and flooring comes from the Tectonics. It gets a lot of nice different colors, especially up in Columbia and Rensselaer County. And then there were some important iron mines. And some of these were in the Hudson Highlands. And after the Revolution, New York State was the most important producer. A quarter of the US output of iron came from New York State. And you maybe heard the story of the big chain that they dragged across the Hudson River to keep the English from sailing up to Albany, was made from iron ore that came out of like Fonstock State Park down in Westchester and Putnam counties. And so these were magnetite mines. Production spiked again during times of economic need, like World War I and World War II, but the last iron mine in New York State closed in the 1970s. So I've got a number of resources, and I made 20 copies of this slide that I'm happy to give out to people. But I'm going to send a copy of this presentation probably to Paul, and he can share it with anybody who might want to see it. And he said that this was recorded on YouTube, but I think sadly it's just a picture of me and not the slides. But I've got a number of resources that you can find information online. The New York State Museum is great. They have a long history of publication of geological papers and studies in New York State, and they're almost all online, available as PDFs. And then this one book called Geology of New York, a simplified account, is another New York State Museum publication, and it's really good. A lot of the figures I showed in this presentation came from there. And then also, if anybody wants to go collect fossils, I know lots of good places to collect fossils. So I'll stop there. And if anybody has any questions, I'd be happy to take questions. I'm sorry I ran about 15 minutes long. Yes. Yeah.
Do we know what the surface area of the continents will be, or starting at the very beginning to most recent one? Changed much?
Good question. Yeah, so he asked, how has the surface area of the continents changed through time? So I didn't go all the way back to the beginning of the Earth, because I started when we have a record in New York. But initially, we believe that the Earth started as a big molten ball. And it was, we say, homogeneous, so undifferentiated in the rock types. The types of rock that make up the continents are very different than the types of rock that make up the oceans. The ocean rock is quite dark in color. It's rich in iron and magnesium, and it's very dense. The rock that makes up continents tends to be light in color, and it's rich in silica, and it's often much thicker. So initially in Earth history, we had a differentiation of oceanic crust and continental crust. And the way they differentiated is that the minerals that make up the ocean rock tend to solidify at a higher temperature than the minerals that make up the continental rock. So if you think of everything in a boiling pot and there's tons of stuff, as you begin to cool it down, the first stuff that kind of skims out are the ocean minerals. And then the last stuff that comes out are the continental minerals as you cool it down. And so during this initial, we say fractionation, when you differentiate oceanic crust from continental crust, you start off and you begin to build smaller or tiny chunks of continental crust. And they're kind of banging around like bumper cars, sort of. And it's a little bit complicated, but also because in the center of the Earth at that time, you had a much higher output of radioactive heat. And so plate tectonics that I said now goes at about the rate of your fingernails growing, back then was going a lot faster. We don't know how fast, but way faster than your fingernails were growing. And so you had these blobs that were kind of going around on microplates. Eventually, as the heat source slowed down in its output, the rate of continental collision and bang around on the crust slowed down, and pieces started to come together, and you started to amass bigger and bigger chunks. And so, long story short, to look at North America and say, what was the size of it before? The West Coast ran down somewhere through about Wyoming, or Montana into Nevada, down into Arizona. And so anything west of there has been added on. And the East Coast ran, as I mentioned, kind of down through about the Hudson River, down to about New York City, and then kind of down through Pennsylvania into Eastern Virginia, and down into kind of Western Georgia. And so anything east of there has been added on. So I would say that we've probably added on maybe 15, 20% of material to North America over time. Oh, the total mass, yeah, of continents. I don't know. That's a good question. Pardon? Yeah, no, you're not robbing Peter to pay Paul, because in this case, you're producing rock from things that are going down, and you can melt oceanic crust, and then it comes back up and can be eroded and just kind of smacked onto the sides. I'll say this, the planet does not get any bigger. So this was a hypothesis for a while that, oh, the planet just keeps getting bigger, right? The oceans get bigger, but we didn't understand, well, one side's got to give and go down somewhere. So that's not happening. We're just kind of moving the continents around. They probably grow a little bit along the edges. I would estimate, again, somewhere around 15% would be my guess. That's a good question. I should go look that up. Yes.
Two questions.
Mm-hmm.
One of them is, in all this story, you have water, huge amounts of water. But probably is there a history of the temperature of that water? Because when you bit wet, you don't boil it. How did it happen? Where does it come from? That's one.
Okay, can I answer that one? Okay, because I'll forget the other one. Good question. We do have a record of the temperature of the water. And we know that early on in Earth history, that water was pretty hot. Because as I said, you had a molten surface, like everything was probably lava on the surface of the planet. As it cooled down, eventually water could begin to consolidate into liquid phase. But then that water was still probably pretty hot. And we do have evidence today of things that can live in super hot water, like at Yellowstone. If you go to Yellowstone, you look at those lakes, the different colors that you see in the bottom are actually different types of bacteria that can live at different temperatures. To fast forward to when things started to cool down, the Earth's oceans, they got hot, and we talk about global warming and climatic warming. We have times on Earth when we think we maybe had no glaciers, like during the Cretaceous, when the dinosaurs, right at the end of the dinosaur time, was probably a time when we had very little ice on land. But usually throughout most of Earth history, we have had places where on Earth you've had continental ice. And so if that's the case, then the Earth's oceans were probably never super hot, but we can get a record of what the temperature was by looking at what we call an isotopic proxy. So that means that if we get a shell, we can look at the amount of different types of oxygen and carbon in that shell. And we can look at when the water's hot, then more oxygen 16 will evaporate, and you'll concentrate oxygen 18. And so or maybe it's the other way around. I can never quite keep those numbers straight in my head. But anyway, you can look at the different isotopes of the elements, and then look at the shells and get an idea of, oh, it was really hot, or, oh, it was really cold. And we do know that there are times, especially in the Devonian that I work on here in New York State, where there were times of global warming. Question 2.
Well, it's related to what you just said.
Mm-hmm.
Besides carbon dating that is only useful when once plants develop the carbon, what other isotopes are used as a dating tool?
Okay, good. Yeah, carbon dating is quite interesting. It only works back about 70,000 years, because after that you don't have enough carbon-14 to be able to measure it. But we can use things like argon, uranium, thorium, potassium, argon, and different isotopes of those that have radioactive half-lives on the scale of like hundreds of millions to billions of years. And so I would say that lead-238 to uranium-238 to lead-205 is a big one. Potassium argon dating is another one. Potassium. Those are isotopes that we use. Yeah. Yes.
So let me give a plug.
Yes. Come on up.
This is great.
Yeah. Here you go.
So I'm going to practice using the mic for next week's follow-on to this amazing lecture, which will talk about the Hudson Valley at the end of the Ice Age. So he's 200 million years. We're talking 20,000 years. And there's remnants that are around, and we'll take an armchair tour of the remnants of the Ice Age in Hudson Valley next week at this time. And I don't think I'll go quite as long unless there's lots of questions, but maybe you'll have them. Thank you.
Sure.
Yeah.
I'll say that you can find some sediments from the glaciers in in the Millbrook Preserve, there's some nice glacial clays that you can find. And I've taken some professors from the art department in there, and they've scooped out clays and they've made some pottery from clays I found around campus in the preserve. Yeah. Any other questions? Well, thank you very much. Very happy to come. Yep. Yeah.